Hello and welcome, Oceanography class. This is the first lecture on Chapter 1, Introduction to Planet Earth. So our world ocean is the most prominent feature of our planet. It covers approximately 71% of the Earth's surface. So if you were kind of a visitor from outer space, you'd be looking at kind of like this blueberry covered in oceans and clouds, and land makes up a smaller portion of that. And the origin of life itself on our planet developed in the oceans. We're very connected to the oceans. In fact, our own body chemistry is very similar to that of seawater. And the oceans have been around for billions of years. They have a long history on our Earth. They dominate the Earth's surface. It's the largest habitat. It contains the largest number of living organisms. And 97.2% of the surface water that's found on Earth is ocean water. So the word Earth, or the way we refer to our own planet, is kind of a misnomer. We really should refer to it as Oceanus, or I don't know, hydrosphere or something. So let's talk about the different oceans. Now, it really is one world ocean. All of these ocean basins are connected to one another, but we give them different names so that we know which area of the ocean you're referring to. So there's four principal oceans: the Pacific, which you can find here, okay, the Atlantic, okay, we have the Indian Ocean, and the much smaller Arctic Ocean up here. We do make a distinction right here. Anything just south of this latitude is referred to as the Southern Ocean or the Antarctic Ocean. And the reason for this is because there's a major shift in global wind belts, as well as ocean circulation, that kind of splits these water masses or makes them distinct from one another. So here on the top, you can see a pie chart of the coverage on Earth. 70% of the Earth's surface is the ocean. So if you just happen to be crash landing on Earth, you would probably hit water. Okay, only about 30% is land. Now, if we break that down into the four different major oceans, the Pacific makes up about half of that. The Pacific is really big. You can actually rearrange all the land masses, and you could have them be kind of fit into the area that encompasses the Pacific. That's how big it is. And that's how crazy it is. Like, if someone gets lost at sea in the Pacific, they might as well just kiss their lives goodbye, because they could be gone there for months. The Atlantic is about a quarter or half the size of the Pacific, and the Indian Ocean is slightly smaller. The Arctic is really small over here, only makes about 3.4% of all ocean water. Okay, in terms of depth, this is depth here. So from sea level, or the surface where we would hang out, down to 4 kilometers here. The average depth, Pacific is the largest and also on average the deepest ocean. Okay, Atlantic is not too far behind, just slightly shallower, as well as the Indian Ocean. The Arctic Ocean is very, very shallow in comparison to the other three major oceans. Now, if we compare elevation, okay, so this line right here designates sea level, so kind of like where we are in Florida. If you go kind of upwards on this y-axis, you're going up in elevation. Okay, so the tallest mountain on Earth is Mount Everest, with an approximate elevation of about 28,000. What is it, 29,000 feet? Yeah, 29,000 feet. Okay, so that's the highest you can get in elevation into our atmosphere on land. Okay, on average, the continents, however, are just kind of right here. Okay, about 800 feet above sea level. And then in comparison, this is the deepest part of the ocean, absolute deepest. This is the Marianas Trench in the Pacific Ocean, and that is 36,000 feet. Okay, so you could quote unquote like remove Mount Everest, drop it off the Marianas Islands in the Pacific, where the trench is, where the Marianas Trench is, and it'll fit. It'll completely submerge itself under the ocean. So that's how deep the Marianas Trench is. Okay, and then here is the average depth of all the ocean. So on average, if you were just to randomly drop somewhere in the ocean, you'd be almost about 4 kilometers below the sea surface. So that just gives you an idea of how vast and also how deep the ocean is. The Pacific is by far the largest, deepest, and it was named by Ferdinand Magellan when he was navigating through the Pacific. He named it after its calm waters in 1520. Okay, the Atlantic Ocean is about half the size, as I mentioned, just a bit shallower. It separates the Old World from the New. The Indian Ocean is much smaller, but it's as deep as the Atlantic, and it's mostly in the southern hemisphere. The Arctic Ocean is a very small percentage in comparison to the other 3 major oceans, so it's also very shallow. There also exists a permanent layer of sea ice that's a few meters thick that sits on top of much of the Arctic Ocean. So that's a layer of ice that sits on top of ocean water. And then there's that designation I mentioned before, the Southern Ocean. That completely circumnavigates the continent of Antarctica, and it's essentially just parts of the Atlantic, Pacific, and Indian. And that line of latitude where that distinction is about 50 degrees south. Then there are the 7 seas. I'm sure you've heard about the 7 seas in perhaps movies or books, or quoted in songs or something like that. But these are large bodies of water that are much smaller than the ocean, and they're much shallower. They all have salt water, but they're usually very enclosed by land, but with at least kind of like a direct connection to the ocean. It's not always the case. One kind of exception is their Sargasso Sea, which is just east of the United States eastern seaboard, and it's given that name because of the sargassum, or algae, that is often caught floating around the surface there. So yeah, these are the 7 seas. Before the 15th century, the Europeans considered these to be the 7 seas. The Red Sea, which is in between the African continent and the Arabian Peninsula, the Persian Gulf, the Black Sea, Adriatic Sea, Caspian, and Indian Ocean. Okay, so here we can see, here's the Caspian Sea is actually a lake, but since the evaporation rates are so high and there's so much input erosion from the local land area, it makes it really salty. Here's the Black Sea, here's the Mediterranean Sea, the Adriatic Sea right here, Red Sea, the Indian Ocean, and the Persian Gulf. And so historically, the reason why these are named the 7 seas is this is largely where civilizations existed that had written history and navigated the oceans, and so they kind of traveled in these areas, and that's why they had they named them the ancient 7 seas. So the average ocean depth is 3,600 kilometers, which is about 12,000 feet. The average continental elevation, places where we live, is about 840 meters. Excuse me, I said feet before, but it's actually meters. This makes it much higher, almost 3 times higher. That would be 2,756 feet. The Marianas Trench, the deepest part of the ocean, is about 36,000 feet. Again, to put that into perspective, what this means, if you've ever been on an airplane, if we'll ever go on an airplane ride again, right? But when you're at your cruising altitude, typically that's between 30 and 35,000 feet. So imagine that. So imagine where you're sitting up there, just munching on some peanuts, that giant bag of peanuts they give you, all 3 of them. You're chewing on that. The distance from you sitting on that airplane traveling 400 miles an hour in an aluminum can towards that distance from there to the surface of the Earth is the same distance from sea level all the way down to the bottom of the Marianas Trench. Okay, and that distance is larger than the tallest mountain on Earth, Mount Everest, which is 29,000 feet. All right, so let's talk about some of the early explorers of the oceans. The oceans are really tied to a lot of human history. A lot of civilizations settled near the oceans for a bunch of reasons. Number one, food, right? Yeah, the ocean provides a lot of really tasty, high in calories, high in nutrient food, oysters, fish, lobsters, whale blubber, stuff like that. It also was very advantageous for trade and movement, right? Once people figured out that they could build vessels and take advantage of currents and wind patterns, all of a sudden you didn't have to walk all the way to go check out your friends in a different town. You could just drift or let the current take you or the wind blow you, right? So the ocean really facilitated a lot of trade and interaction between the cultures. So that's why that was very prominent early on in human history. Some of the best navigators and the earliest navigators really were the Pacific navigators. Now we know today from genetic studies, if we look at all the different islands leading off from Southeast Asia and into Micronesia, here's the Marianas Trench, by the way, so Guam and the Marianas Islands are over here, including Melanesia, all the islands here, New Zealand included, Fiji, and here's Australia, and then going into, or here's New Zealand, sorry, and into Polynesia. Genetically, all these people are very similar, and they didn't evolve on their own, isolated from other peoples. And what that means is that the very first travelers from Southeast Asia, they basically made it to all of these different islands in the Pacific Ocean and basically island hopped and moved around. Okay, so these were voyagers. We were voyagers, right? And these voyagers were skilled, daring. They took chances, and I'm sure a lot of them, perished at sea looking for a new island to colonate. But obviously, many were very successful because there are many different people and cultures inhabiting all of these islands that are here. But based on archaeological evidence, here's the timing of their arrivals. Okay, and these change if there are new discoveries, but in Micronesia and a lot of the islands over here, there's evidence that there were humans here 4,000 years before the Common Era. Okay, and then going further and further away into towards Polynesia, then 1,000 years before the Common Era is where we see Fiji, for example, colonized. New Zealand down in this way, 800 after the Common Era. French Polynesia, 30 BCE. The Hawaiian Islands, about 300 years after the Common Era. Okay, and then Easter Island, about 1200 AD. Okay. So there really isn't any written records of their history, so it's very difficult to piece together how they navigated this area, but they were incredible. Some of the things that they've discovered are these really cool maps, so to speak. It's almost like an ocean guideline. It's a bunch of kind of palm twigs tied together. And it might not look like much, but what it is what it indicates to these navigators are different patterns of open ocean waves. Okay, so these people were really in tune with the ocean. When they would go out and navigate, open ocean waves would approach and hit the ship, right? For us land lovers, that would just make us sick. We'd be thrown up overboard. But to these people, they could interpret the waves that were coming towards their boat. And normally in the ocean, you have open water waves kind of coming towards you and hitting your boat. But sometimes as waves are kind of traveling through the open ocean, they'll interact with land masses and they'll bounce off of them or they'll refract off of them, and that changes the pattern of the open ocean waves. And so what this guide essentially indicated to these travelers, where if you see this pattern of wave diffraction, go in that certain direction and you'll find a landmass. So that's how they think, our archaeologists think, these pretty skillful navigators interpreted the ocean to find new land. And so the idea is a lot of these voyaging cultures maybe would inhabit an island, and their population would grow and kind of exceed the carrying capacity of the island that they lived on. So they're kind of forced to navigate and colonize somewhere new. And so that's why they'd send kind of like a group or settlement out to a new island. Okay. So with new genetic studies, scientists have kind of pinned down that all the populations that have inhabited New Zealand, native populations that inhabit New Zealand, Australia, New Guinea, Fiji, Hawaii, they're all descendants genetically from people that originated in Southeast Asia, specifically areas near Taiwan, which is pretty cool. And that was, a big step in the research and understanding. But before that, there was this one researcher from Norway who was convinced that perhaps there were kind of two competing theories. One was the way people navigated to all these islands in the middle of the Pacific Ocean was through Southeast Asia, island hopping and navigating that way. But Thor Heyerdahl suggested that perhaps some native cultures from South America made it to like Easter Island and then perhaps to Hawaii or something like that, that was proposed. So he actually wanted to demonstrate that. So he built his own balsa raft, which you can see here, and he left from South America and made it to Easter Island, which was an amazing journey. But ultimately, through genetics, they kind of proved that the native people from South America aren't related to the Polynesians. Okay, so let's jump over to the European navigators much later, closer to 2,000 years before the Common Era. But the Phoenicians were credited with kind of like being the first explorers in Europe, the first in the Western Hemisphere. I mean, and they get the credit because we have written history and evidence of it. And they explored the Mediterranean Sea, the Red Sea, the Indian Ocean. They were the first to circumnavigate Africa, and they even reached the British Isles. The Phoenicians also developed our alphabet, right? And the reason why that's important is because in order to kind of trade with different cultures, you kind of have to develop a system where you can, trade on or communicate on even terms. And so developing a language and writing stuff down was really important. So there's a lot of written history of travels, ship logs, and materials like that. And those were the Phoenicians. And the Phoenicians are found in like kind of present day Egypt, Jordan, Israel, that kind of region. Okay. The Greeks kind of came afterwards, and with the Greek civilization, there was a huge rise in scientific thought and great kind of institutions were being built, like the Library of Alexandria, and there was a lot of progress in terms of scientific progress, and they used these technologies in their sailing. And the Greeks sailed northward using a very simple way to determine the latitude that you were at, meaning like how far north or south you were on our globe. Okay, and the way you do that is by using the North Star. So wherever you are, let's say you're here, the North Star is approximately kind of like on our axis that goes right through the sphere of our Earth. And so if you're at a more northern latitude or closer to the kind of the northern or the North Pole, Polaris will be higher up into the sky. If you're closer to the equator, Polaris will be seen closer to the horizon. And so that angle, right, that's this angle here, you can measure that. If you're on a boat, you can measure the angle difference between the horizon and the location of Polaris. So if Polaris is higher up in the sky, that means you're at a more northern latitude. If Polaris is down here at a really just above the horizon, that means you're pretty close to the equator. So you can determine your latitude based on that angle. Okay, but you couldn't at that time. They didn't know how to determine longitude, meaning your east-west. That was developed much later. And back then, okay, this is 300 years before the Common Era, the Greeks knew the Earth was round, okay, and it was determined by Eratosthenes. He basically used simple geometry, and he compared how a stick cast a shadow in one town versus another town, which a known distance away from that stick, and at the same time the sun kind of directly shone through, directly above a well, and he used that to calculate the circumference of the Earth. He came up with a number 42,000 kilometers, right? 300 years before the Common Era. And the true number of the circumference of our Earth is 42,032 kilometers. And that is remarkable that he was able to calculate with that level of accuracy 300 years before our Common Era, which is pretty incredible. Later on, there were other Greek scientists who updated erroneously Eratosthenes' circumference measurements. But what they did do was provide the most accurate quote-unquote world map, right? Because this was their world at the time. They couldn't really explore much farther than this. But they were able to draw longitude and latitude lines, which was pretty impressive for that time. Okay, this was in 150 AD. So Ptolemy updated the circumference estimation, and that became that was used by Christopher Columbus as he believed the Earth was much smaller than it was because of this erroneous calculation, and that's why he thought he can make it to Asia by sailing west in the Atlantic. Okay. And then so the Middle Ages came about, and there was a big tragedy. The Library of Alexandria burned down because there was a rise in the beginnings of Christianity, and they kind of took down the Roman civilization, burned down the Library of Alexandria, where all these ship logs and poetry and literature and mathematic documentation was stored, and so all of that precious information was lost, and the Western Hemisphere kind of dipped into the Dark Ages. But there were a few Arab scholars that actually copied a lot of the information from the Library of Alexandria, and they took that with them. And then they became, and used that knowledge, became the dominant navigators in the Mediterranean Sea. And so they traded with East Africa, India, and Southeast Asia predominantly, and they took advantage of the monsoon winds to travel back and forth, kind of seasonal travel, because the winds kind of shift. So when the monsoon winds come in, then they go into India, they dock there for a while, bring in materials and trade things that they want, buy some other things that they know at home that they would want to buy, and then when the winds shift, they would go back home. So Arabs during that time became the dominant navigators in that region. In a different, kind of completely different area in Northern Europe, the Vikings explored Iceland and Greenland in the 9th and 10th centuries AD. Leif Erikson looked at, made it down to Canada and Vinland, which is now known as Newfoundland. by 995 AD. Okay, there were actual settlements in Greenland and in Newfoundland in 1450 AD. People are Viking explorers after Leif Erikson, I'm going to butcher this name, but Bjarni Herjolfsson, they actually developed settlements. But the problem was they had some pretty bad weather. Some of those years there was some pretty bad winters, and their bad farming practices, and those settlements kind of died out. But the Vikings are actually credited with the first kind of European cultures to settle in the Americas. Not really Christopher Columbus, but the Vikings were actually there first. So they were pretty good explorers. They don't get the credit, I guess, that they deserve. But here's the Viking homeland. Made it to Iceland, Greenland. Here are some few settlements over here. They think they explored areas into Baffin Island in Canada. And then here are those settlements in Newfoundland. Okay, but those largely weren't successful. They didn't stay long, and people there probably died out. A combination of really bad weather, cold winters, and stuff like that. Okay, and then Europe came back into the picture. There's the Age of Discovery, 30 years from 1492 to 1522. What happened here during this time was that Constantinople, major town in Mesopotamia, had a major power shift, and the trade routes were kind of cut off. So a lot of Europe had to find new ways of trading with Asia. And so this is what kind of sparked the interest in finding new routes and the need for good navigation and good sailors. And so the Portuguese started kind of training people and develop an academy to kind of develop the next generation of explorers. And one of the first was Prince Henry, the Navigator. Okay, and under him, other explorers kind of trained under him, like Christopher Columbus, and they were set to explore kind of different trade routes. The most common one was to kind of circumnavigate Africa and go that way, but that was a pretty long and dangerous journey, and so that's why Christopher Columbus was able to finance a shot in the dark kind of route, and the Portuguese actually didn't finance it, but he was able to talk to the Queen of Spain, and they financed his trip. And so he went out and landed in Hispaniola, which is present-day kind of Dominican Republic and Haiti, and he kind of found that and committed atrocities. He did some pretty bad stuff, and kind of made a few journeys back and forth about 3 times, but he actually never set foot in North America. He kind of only set foot in the Caribbean. Okay. Then later, Ferdinand Magellan was the first to undertake the circumnavigation of the entire globe. Okay, he went on a group of 3 ships and 280 sailors, and it took him, I think, 3 years out in the ocean, and he was killed on a Pacific island in 1521. And 1 ship made it back to Spain, and it had 18 sailors. So what are the odds of surviving that journey? Pretty bad, right? Then Juan Sebastián de Caño completed the circumnavigation in 1522. Okay, and those voyages really paved the way for the Spanish to kind of rule the seas at this time, and they just absolutely exploited the new cultures that they found in the Americas and the Caribbean. They essentially just took all the gold and silver as possible to go feed the greedy, monarchs that they were serving, right? And so they committed atrocities in Central America and in South America. And so their dominance during this time ended when English and also Dutch ships which were smaller and also more maneuverable compared to the giant Spanish galleons. So what the English and Dutch essentially did were like, oh, okay, we'll just rob your ships and they'll take all the gold that they took from people in the Americas. And so they defeated the Spanish Armada by 1588, and then England essentially became the world colonial powers at the time when they defeated the Spanish Armada. Okay, so here are the voyages of Columbus. See, Columbus just kind of went down, boop, made a stop and came back. Right, did that I think 3 times. And then this is Magellan's trip. So he went to Rio, right? Straits of Magellan, named after him, and then went to the Pacific Islands. He was killed here, and then his crew kind of did the last little leg of the trip and circumnavigated the globe, which was a big deal. All right. Took him 3 years to do it. Imagine giving up 3 years of our life just to do that. And probably dying, right? I mean, odds are, I would most likely die. I get very seasick. Anyways, so the English, they wanted to retain their kind of maritime superiority. And one of their best navigators was Captain James Cook. And the English were almost like the first navigators to go on voyages that were strictly for scientific purposes. So instead of just kind of going out and creating settlements and colonizing and exploiting different areas, they actually sent out ships to find out new information. Things like finding perhaps a pass through like the Northwest Passage through Canada, finding new islands. One of the trips James Cook took on was to go to Tahiti and watch Venus's track across the sun, because they wanted to accurately measure Venus's orbit at the time. And he captained the HMS Endeavour, Resolution, and Adventure. And they measured a lot of ocean characteristics, like sea surface temperature. They also did soundings, which are a measure of the depth of the ocean, which hadn't been done at the time. And they benefited greatly from new technology, the chronograph. This was developed by a cabinet maker in England. It's essentially a watch. And by being able to kind of tell time independent of where you are, you can determine how far you are east and west, and not just north and south. So that was a key development in being able to kind of pinpoint your spot or your location on Earth using longitude and latitudes. In fact, the English came up with that. Okay, here were Cook's voyages. Traveled in a lot of different areas in the Pacific Ocean. And he was interesting. You can he kept a really detailed journal, which is pretty crazy because it's very interesting. You can read his journal because he encountered people in the Pacific that had never met any other person ever. So it was kind of like the first encounter of, like, basically these strange white people showed up out of nowhere in this giant wooden ship and then interacted with locals. So he has interesting insights and interactions with native people. Ultimately, he died in a skirmish with native people, most likely some sort of miscommunication, or I don't know what happened. But he died as a result of a skirmish somewhere in the Pacific. He's also credited with a lot of sailors before the English kind of dominated the seas at this time. Sailors suffered from scurvy, right? And Pirates of the Caribbean really fantasizes what it was like being a pirate or being out in the ocean. But scurvy was a pretty big deal and actually killed more sailors than shipwrecks and encounters with natives and other perils that are in the ocean. And essentially what scurvy is a deficiency in vitamin C. What happens is your teeth start turning black, immune system goes down. It's pretty nasty. Being a sailor back then was horrible. So what he figured out was he improved his sailors' diets by introducing sauerkraut. I don't know if you've ever had sauerkraut before. It's kind of like that. It's like a like pickled cabbage essentially, but that is loaded with vitamin C, and it's also can be stored for a long time. So you can be on a ship for 2 to 3 months and still be able to eat sauerkraut. And that actually improved the diet of his sailors and increased the rate of survival for sailors that went on these journeys. Okay, so oceanography continues today. Obviously today we have a lot better technology. We have sonar, robotics, satellites, computers, right? We have the National Oceanographic and Atmospheric Administration. That is a great agency that helps us predict ocean conditions and tracks hurricanes and stuff like that. And so finally, here we are, 30 minutes in, and yeah, you might be wondering, what is oceanography? But oceanography is kind of like an interdisciplinary science that includes all kinds of different sciences together. In this class, we're really just we're going to skim the surface of a lot of different areas of science, and I'm going to try to dive deep and get some meaningful context in a lot of these subjects. But it covers geology, okay, seafloor tectonics, sediments, geography, wind belts, weather. Another science that's very important here is biology, fisheries, the ecology, microbiology, chemistry of the oceans, physics of the oceans, thermal properties of water, waves and currents. And then astronomy is important too, because that controls tidal forces and origins essentially. And so scientific inquiry is just essentially the phenomenon of trying to understand the physical processes on Earth and being able to predict what will happen as a result of that understanding. Okay. The physical properties that we witness today, processes that we witness today, are similar than the ones that we've seen in the past. Okay. And so science tries to discover these and then make predictions. And we do this in kind of a logical method called the scientific method. And once observations and hypotheses have been made and then have been tested, vigorously tested, will you come up with a theory. And a theory is a well-substantiated explanation of some sort of aspect in the natural world. Okay, so here's that process. You start off with observation. The book does a pretty good job of an explanation. Like whales. Have you ever seen that Prudential commercial where the humpback whale kind of jumps out of the water and breaches and then smacks itself back down? That's an observation, right? And scientists and regular people and sailors have always observed whales breaching in the water, kind of jumping out of the water and smacking back down. That's an observation, right? Why do they do that? That's an important question. Why do whales breach? And so you try to come up with explanations or hypotheses on why they do that. Do they breach because they're communicating with different pods of whales in really far distances? Are they trying to smack parasites off their back or something, right? And this is something that scientists have kind of been asking. And they did a lot of research and testing, and that's this process, to test whether or not their explanations for that behavior are right or wrong. Okay, so and so what scientists have done after studying weeks and weeks of different pods of whales breaching and collecting data on that behavior is that the whales actually use breaching as a form of communication. So when pods are kind of close together, they'll do that fin slapping, their caudal fin, they'll bring it out of the water and then slap. And so that's how they can kind of make noise and communicate with pods that are close together. But if the pods are very far apart, or there's a lot of noise in the ocean, like ships or something like that, then they'll breach. Because breaching, you know, they're taking their giant bodies out of the water and then they're smacking down the water really hard, like a hammer. And that makes a louder noise so that they're able to communicate over longer distances. Okay, so only after a lot of testing do you have a theory, okay? And then perhaps we'll call that the whale breaching theory, Okay, then you can use those theories to kind of predict perhaps future observations. Okay, all right, so let's talk about the formation of Earth and our solar system. The Nebular Hypothesis is a hypothesis that all bodies in the solar system formed from a nebula, and that's a cloud of gases and space dust. Space dust meaning like material like silicate material, rock material, metals, and gas, kind of in this giant gaseous three-dimensional nebula like you see there. The composition of this nebula was mostly hydrogen and helium. Okay, but as everything kind of in this gaseous nebula has mass, it exerts a force of gravity, things start kind of contracting to one another. At the center of the nebula is the proto-sun, or the proto-sun begins to form. So essentially, gravity concentrates a lot of the material at the center of the nebula, and the cloud starts to kind of collapse into the form of a disk. And then it begins to rotate. And as it rotates, it kind of induces more collisions of this mass material, you know, a lot of that dust, a lot of the gas, and surrounding the largest mass in this disk are protoplanets, including Earth. So Mercury, Venus, Earth, and Mars are kind of the interior rocky planets. They're rocky because they're closer to the sun, and the heavier materials that coalesce to form the protoplanets closer to the sun was hotter, so the heavier materials condensed closer to the sun. And then the volatiles, or the gases, those condensed further away from the sun where it was cooler and kind of formed ice. And that's why beyond Mars in the asteroid belt, you'll find the gas giants. Okay. So this started to rotate and started to form our very first planet, as well as our proto-sun. Okay. And our Protoearth formed, and initially, as it formed, it was kind of a really hot, kind of silicate, rocky Earth that was kind of like a magmatic ocean, and it just slowly started to cool down. It was a lot larger than the Earth today. Its composition was homogeneous, meaning that it was kind of all one composition, very well mixed, and it was bombarded by meteorites. And meteorites are just kind of leftover portions of planetesimals that, you know, weren't part of planets. So there was a lot of collisions, and that kind of really heated up the Earth. One planetesimal that was much smaller than the Earth was also kind of orbiting the sun, but it was in the direct path of our Earth, and it struck our Earth, right? And that collision kind of added a lot of material to our Earth, and then the rest of the material got caught in Earth's orbit, and that became our moon. Okay, so our moon's origin story essentially is a collision course with Earth. Boom, there you go. And there's an artist rendition of what happened. And then as the Earth heated up, a lot of the lighter material, or lighter elements, started to kind of float towards the outer edges of the Earth, kind of from the interior. A lot of the denser material, like iron and nickel, because it's heavier and denser, and when you heat something like that up, it sinks towards the center. It's like if you boil milk, right? If you boil milk, the cream rises to the top. That's the lighter material. So the light, oxygen, silicon, potassium, a lot of the lighter elements started to kind of rise up, okay? And this led to what we call the density stratification of our Earth, meaning now the Earth was becoming heterogeneous, meaning that it was forming distinct chemical layers in our Earth, okay? All right, there we go. And here's our solar system today. There's our sun, 4 interior rocky planets. Here's the asteroid belt. And then beyond this, then you start having the cooler gas giants, right? And then here's the Kuiper belt way out here. All right, so the density stratification, here's showing you the different layers that formed early on in Earth's history. And this was a result of gravitational separation. So the high density materials like iron and nickel settled into the core. Okay, so here's the surface of the Earth. All right, and then we have our crust and lithosphere. Here's the mantle portion of our Earth, and here's the outer core. So all of this here is made up of iron and nickel. Very dense material sank towards the center of our Earth. So here's the distinction: early Earth. Here's the proto core, molten iron, and here's our magmatic ocean. Right. So this is very early on in Earth's history. This is the layers of our Earth today, and we'll go into this in more detail. So less dense material formed spheres around the core. Okay. So there's two ways we can identify the internal structure of our Earth. One is through the chemical composition, and the other is through physical properties. Physical properties is essentially how the material behaves. So there's the lithosphere, asthenosphere, upper mantle, lower mantle, and core. And then if we're talking about chemical composition, we got the crust, mantle, and core. I'll show you other pictures. So if we look at the layers of our Earth based on chemical composition, meaning like the different layers are differentiated by their chemistry, the outer and kind of thinnest layer is the crust. That's a very low density, mainly silicate rocks and silicate minerals, very light materials, silicon, oxygen, potassium, calcium. Those are the typical light elements that you'd find in the crust. Below the crust is the mantle. This is also rock, silicate rock, but this silicate rock contains more iron and magnesium. And iron and magnesium are heavier. So that's the distinction between mantle and crust, is that there's more iron and magnesium in these rocks versus the crustal rocks. And then when you get to the core, the kind of last layer, this is really made up of high density iron and nickel. And that's how it differentiates itself from the mantle and the crust. Now, if we look at the Earth's layers based on the physical properties or how the material behaves, the outer layer is referred to as the lithosphere. The lithosphere is a material that is brittle. It breaks when it's under stress, right? That's why we have earthquakes and stuff like that. So it's very rigid. And that's typically the upper 100 kilometers of the Earth. So from the surface, the bottoms of the oceans, or from the continents, so it's the crust plus the upper portion of the mantle is considered the lithosphere. All right, so on average is about 100 kilometers. So that's the lithosphere right here. All right, below that is the asthenosphere, and that's exclusively in the mantle. Now the reason why it gets its own kind of distinguishing layer is because it behaves differently. The asthenosphere is hot. The rocks are very close to their melting temperatures, so that makes it very weak, and that stuff is plastic and can move around. Okay, and so essentially that creates a division between the lithosphere and the asthenosphere, and the lithosphere can kind of float on top of the asthenosphere. Then as you go deeper and deeper within the Earth, you run into the mesosphere, which is this area right here, and that's also in the mantle. So it's just mantle rock, but it becomes more rigid, and the reason why it becomes more rigid is because of the increase in pressure. Okay. Then once the mesosphere is over, you get to the outer core, and the outer core is kind of its own distinct layer because it's actually liquid. This is liquid iron, and it kind of moves and convex. Okay. So this is the outer core, liquid iron. And then the inner sphere here, the iron, because of the increase in pressure, the iron actually solidifies, and this is a solid. So the inner core is solid. Okay, so these are the layers based on how the material behaves. All right, just to reiterate, here's the lithosphere, a cool rigid shell surrounding the Earth, on average 60 miles thick, includes the crust and upper mantle. Okay, so here's the upper mantle. This is the lithosphere, ocean crust and continental crust plus upper mantle. All right, then the asthenosphere, hot plastic mantle material. That's this area here. It's deformable, capable of flowing because it's very weak. Okay, and that goes from the base of the lithosphere to about 430 miles below that. So it's a pretty prominent layer. There's two different types of crust. There's continental crust and there's ocean crust. The rock that makes up continental crust is granite, right? So think of your countertops in your kitchen. That's granite. That's an igneous rock, or a rock that formed through the cooling of magma. Basalt's also formed from the cooling of lava on the surface of the Earth. But basalt makes up the ocean crust. So if you go out into the oceans, go to the bottom of the ocean, the sea floor, get through all the sediment, you're going to run through a bunch of basalt. And this is a volcanic rock. And it's kind of black in color. Okay. And the main difference is that basaltic rock is a lot denser, meaning it's heavier than granite. Okay. So when you're talking about the ocean crustal thickness is about 5 miles, while on continents, on average, is about 22 miles. So there's a big difference there. All right, what's the origin of our atmosphere? Well, it formed through outgassing. That's a process where carbon dioxide, water vapor, hydrogen, sulfur dioxide, other gases are expelled from fumaroles or volcanic vents, or hydrothermal activity at the bottom of the ocean. This is where our atmosphere originally came from. And our early atmosphere, it was very different from our atmosphere today. Didn't have any free oxygen. So as these volcanic eruptions kind of delivered gas into the atmosphere, obviously got caught by Earth's gravity and then kind of trapped there. A lot of the water vapor that was coming out of it as a gas condensed in the upper atmosphere and fell back as rain. And that's what formed our first kind of pooling water in the low areas of our early Earth. Okay, and permanent oceans formed as a result of this repeated process about 4 billion years ago. The reason why the ocean's salty is because that rainwater dissolved the exposed rocks, and the kind of weathering of the exposed rocks brought a lot of the dissolved solids into the water, and that's what makes it salty. Okay, so this is an artist's rendition of what early Earth would have looked like. Life showed up, the Earth's formation was about 4.5 billion years old, and the oldest evidence of life on Earth that's fossilized are these stromatolites. These are bacteria that lived in shallow parts of the ocean. Right here, they lived in kind of bacterial mats and created these mounds. And these are fossilized in a lot of rocks. This organism still exists today. You can find it in Australia, Shark's Bay, Australia. But essentially, they live in these shallow waters and they photosynthesize. Okay, so they're these fossilized organisms that lived on Earth 3.5 billion years ago. Single-celled bacteria. But earlier than that, there's other evidence of burrowing organisms. But scientists think that even earlier than this, about 500 million years before stromatolites showed up in the fossil record, there must have been Archean bacteria that existed in kind of really inhospitable environments, like hydrothermal vents at the bottom of the ocean. It was likely a starting place for a lot of organisms. Okay, oxygen kind of showed up much later. It was a major oxygenation event. Humans require oxygen. Try to go without some for a few minutes. It's terrible. But the reason why oxygen started to show up in our atmosphere is because of photosynthesizing organisms, kind of like those stromatolites in the ocean. They're one of the first organisms that evolved to undergo this process of photosynthesis, where they convert carbon dioxide and they excrete oxygen as a waste product and create carbohydrates that they use for food, or sugars. And so that process of photosynthesis created a lot of free oxygen, and initially all the free oxygen would react immediately with iron in the ocean and then deposited out as sediment. So it took about like 1.2 billion years of organisms on Earth consistently photosynthesizing to actually start to change the composition of the atmosphere. And once free oxygen started to form in the atmosphere, ozone began to form in the upper atmosphere. And that was a huge step for evolution of early organisms. Because the ozone layer will filter out a lot of UV radiation, and if there's less UV radiation striking the surface of the Earth, then that allows for kind of organisms, single-celled organisms, to proliferate and even evolve into multicellular organisms. Okay. In the beginning, we didn't have an ozone layer, so a lot of the organisms, especially the anaerobic bacteria, which require little oxygen, may have helped originate life. In fact, this guy, Stanley Miller, he's a scientist who, as a graduate student, came up with this experiment where he kind of simulated Earth's early atmosphere, okay, then added some electrodes to signify like kind of like lightning strikes. And so that mixture was carbon dioxide, hydrogen, methane, and ammonia, something you typically see. And his kind of result of doing this experiment were organic molecules were created. So he kind of created something almost out of nothing. And that's believed to be kind of like the conditions for how life began in early Earth. He kind of mimicked that. Pretty famous experiment. So what that led to, we had living things on Earth, initially very simple, single-celled prokaryotes, but then what happens is they reproduce, they evolve, they change, and organisms adapt to different environments. Luckily, the ocean's a very well, ubiquitous, but also an environment where there isn't much change in daily temperatures. It's a very kind of stable environment, and that allowed for organisms to kind of proliferate in all areas of the ocean. But then they started to adapt and change to different environments. And so what happens with evolution is organisms that just so happen to have advantageous traits, which could happen just through genetic variability or some sort of fortunate mutation, they're quote-unquote naturally selected, meaning that for whatever reason that trait might help them survive better, and then they can pass that trait on to their offspring, and then that offspring can proliferate, and so on and so forth. So those traits are passed on to the next generation, and then they become more successful. And that's how organisms adapt to environments. And then eventually, once the organisms become so abundant and proliferate, they can actually modify their environments. Okay, so that's how evolution and natural selection work. Heterotrophs are kind of the very earliest form of life. Okay, they require an external food supply, meaning like they need to like bump into other things to kind of consume food. Later on, autotrophs evolved later, which are organisms that manufacture their own food. Think of those stromatolites building those mounds and photosynthesizing. The process of photosynthesis is manufacturing your own food supply. So they don't need anybody else, right? So the first autotrophs to form were very similar to anaerobic bacteria. These organisms live in environments with very little free oxygen. Okay, so today's day and age, I mean in deep underground or in environments that are with very little oxygen, kind of unusual environments, we still see them today. But they actually, some have evolved to generate their own food, kind of like photosynthesis, but they don't require the sun. It's called chemosynthesis. And they actually use chemicals from volcanic or hydrothermal vents to create sugars to manufacture their own food. So once we discovered this, by the way, which we only discovered these organisms in the 1970s, that supported the idea that perhaps the origin of life on Earth was through these anaerobic bacteria in these kind of hydrothermal vents at the bottom of oceans, because that's a likely environment that would have existed 4 billion years ago. So those are the first autotrophs. And then later on, organisms kind of evolved to be more complex. Eukaryotes showed up, which are single-celled organisms that have a nucleus and a bunch of different organelles that perform different functions. Then that evolved to multicellular organisms. And then there's, photosynthesis was occurring before then, but those complex autotrophs developed chlorophyll. And that allowed the use of the sun for photosynthesis and created this process of photosynthesis to create sugar and excrete oxygen gas and put that dissolved oxygen in the water to allow for other organisms to respirate, right? Other organisms in the ocean, when they move through the water, they're able to use that dissolved oxygen to breathe, right? And then they excrete carbon dioxide and gas into the water, and then that carbon dioxide is used up again by these small autotrophic organisms here. Okay, so after the formation of the arrival of stromatolites in the ocean, and they began pumping a lot of oxygen into the atmosphere, it took about a billion years of this occurring on Earth to increase the oxygen so much that oxygen was present in the atmosphere and formed an ozone layer. And the reason why we know this is because there are these deposits called banded iron formations. You can see this here. These are deposits of iron at the bottom of the ocean. And the reason why these deposits are here is because all the free oxygen that was pumped into the ocean would immediately be used up into the sediment and deposited, right? All the free oxygen. But as soon as enough oxygen was being used up and not bonding with iron in the water, then it could go into the atmosphere, and these deposits no longer exist. So these deposits stopped about 2.5 billion years ago, or that's the youngest deposit we can find of banded iron formation. This is a typical iron ore that we mine. Okay. And sadly, what happens a lot in Earth as the environment changes, there's major mass extinctions. The anaerobic bacteria now, with all this free oxygen in the atmosphere, had fewer and fewer environments to live in, so they kind of died off. Okay, the Earth is 4.6 billion years old, and we know this because of radiometric age dating. Okay, that's the spontaneous decay of radioactive elements. All right. As one example is uranium-235. This atom is so large, its nucleus is unstable, so it'll undergo radiometric decay, and it'll spontaneously shoot out parts of its nucleus outwards and decay into a new element. But it happens at a predictable rate, and a rate that we can calculate. And if half of those atoms decay into its daughter isotope, which is lead-207, that's called 1 half-life. Okay, so if you have 1 million of these atoms here, 4.2 billion years ago, after 1 half-life, about 700 million years have gone by. And you can keep doing this half-life game up until 6 half-lives, which is today. And so essentially you can age date a lot of volcanic rocks. You can age date meteorites. That's what we've done. We've age dated a lot of the the floating material that didn't coalesce into a protoplanet that's part of the asteroid belt and have landed on Earth. They all come up with the same date, and that's 4.6 billion years. And so that's how we know how old the Earth is. And through that information, we've been able to, geologists over a long period of time have, through, and also collecting fossils and putting rock units in terms of age relations, in terms of relative dating, like what's older, what's younger, putting that in order, and then later on assigning radiometric dates. Here's the entire geologic timescale from the origin of Earth 4.6 billion years ago to the first organisms with shells to show up in the fossil record 542 million years ago, right? So here's the entire geologic time scale to scale. So most of about 4 billion years of Earth's history has been very simple life forms. Okay, no fossil record whatsoever. All right, remember 3.5 billion years ago, right around here is when those photosynthesizing cyanobacteria showed up. But as far as the fossil record, nothing showed up until about 542 million years ago. And then here, this is the extent of our fossil record. And the first trilobites were dominant, first fish showed up, first land plants, fish become dominant in the oceans, insects show up. Ugh, why? Amphibians become abundant, start taking up those coastal environments. There are large forests that eventually become coal swamps that we're mining out today. First reptiles show up. There's a major mass extinction at the end of the Paleozoic. 90% of ocean organisms go extinct, which is pretty crazy. Dinosaurs show up then. The first birds and the first mammals show up in the Mesozoic. The first flowering plants show up in the Mesozoic. Another major mass extinction. See you later, dinosaurs. The non-avian dinosaurs. Birds are considered dinosaurs. They live on. And then humans develop really late in the game. All right, so that's the history of our Earth.